Hey everybody, good morning. Let's start our today's class. Uh, I I think you guys can see my
Good
sharing.
morning, sir.
Okay. Actually, you guys can see that. Uh, I think Mr. Cater said, "Teacher, can you please shortly explain chapter 7, 8, and 9 again before tomorrow's class?" I think maybe this three chapters is very difficult for you guys to totally understand. Uh, I uh, I think um, I think actually we have to do this kind of review last time, you know. So back to maybe last time, we have reviewed chapter 5, 6, and 7, right? Just write on a whiteboard to give you all the main knowledge points of these three chapters. So today I think I better change the way, maybe chapter 7, 8, and 9 too difficult for you guys to totally understand and to finish some examples of homework by yourself. So actually, I think you guys can consider that you can read our textbook, right? I think all you guys should have this textbook. Okay, I have sent to our WeChat group. So I think today maybe I will take some time to review these three chapters just to use this textbook. And since we don't have enough time to stay long enough on these three chapters because we also have the third part, dynamics, to learn together. So maybe we will quick review these three chapters first. If we still have time today, we'll move into the new things. We'll continue to learning dynamics, right? So I hope you guys can look this screen clearly. Actually, this is our textbook. You know, from chapter 7, we have learned basic motions of a raised body. So since you guys want I give you a quick review, so I can just use this textbook to review some topic we have focused before, right? So the first section on this chapter 7, we have learned translational motion of a raised body, right? We have learned the translational motion of a raised body. So actually, translation is a special case in which the body moves without rotation. That is, we can choose arbitrary line like AB on this body. So when this body moves from one position to another position through a time interval, so if you look the original position of AB and the new position of A prime, B prime, you will find actually the orientation of A prime, B prime will always equal to the original position of AB. That means this body will never rotation, right? Will never rotation. So we call that this kind of movement is translational motion. This is the simple list motion of a rigid body，它是钢体最简单的运动形式，对不对？如果 if you know that the rigid body have a translational motion, then you will immediately remember that there are two main characteristics is I'll try to write, but it's not good to use this pen. Actually, we can have this conclusion. If this rigid body has translational motion, we will always have this conclusion. Any 2 point, right? Any 2 point. You know, it's hard to use this, so I have to use my mouse to write, but it's very difficult. So any arbitrarily selected 2 points on this body will always have the same velocity and same acceleration, right? That's what we have learned before.
So the main characteristics of a body which has translational motion is any 2 points will always have the same velocity and the same acceleration, including its direction and magnitude. So this is a very important thing you guys should know. I think I have repeated that several times, right? And you guess you should better know a lot of in our daily life something maybe can consider look at a rigid body like this car when it move from right to left maybe with the velocity v. So uh, we can look at this car is a translational rigid body, and this is a very typical mechanism we all should know. Actually, you can look at this. This link is parallel to this link, and this is parallel to this link, right? And the length of these two bars are equal. The length of these two bars are equal. So we call that translation of a parallel link. Actually, this is a parallelogram, right? So this link, which do not connect the frame directly, actually it connects this rigid body and this rigid body. And this link, it will have a translational motion. So you guys can look at the translation of the parallel link swing plate. So we can use this characteristic to move maybe this something from this position to another position. Actually, this is a cylinder. Actually, it will push this mechanism to rotate some angle from one position to another position. So this weight can be transferred from this position to this position, right? And you guys can look the third picture, translation of operation valve moving in space. You know, so this is the car, and that is the position. Maybe it's more like a chair. Some a driver is sitting on here. So actually, this movement also is the translational motion. And these two wheels, two pair of wheels, actually is our train, the reel of our train. Actually, the wheel, its movement, we can see actually here also is a parallelogram. So from this section, you should know what is translational motion and the main characteristic of translational motion is what, right? So this is very important. You guys should know. The second section of this chapter 7, we have talked about the second type of basic motion of a rigid body. That is rotation around a fixed axis. So maybe after today's class, if you guys still has a lot of confusion about 7, 8, and 9 chapters, you guys can try to read the textbook by yourself. Since we don't have enough time to read all the paragraph in detail, we just pick up some very important paragraphs to repeat it again. But you guys can take your time and read the whole chapter, uh, right? Maybe it will help you have a good insight of um, these 3 chapters. So when we talk about the rotation around the fixed axis, so we can look at the first paragraph of this textbook. Rotation around the fixed axis is the motion in which one line in the body. So you can, yes, I only have time to review the key points, right? So I cannot cover all the aspects of these 3 chapters. Uh, it will take 2 times, and we have a lot of things to learn. So rotation around the fixed axis means you guys can look at this. If we see this arbitrary shape is a rigid body which has rotation around the fixed axis is this axis Z. So you can think we have axis Z, which is pushed into this body. It must have a line coincide with this axis Z, right? Then when this body rotation around this fixed axis, this line, although it is the line on the body, but it will fixed, right? It will fixed. It will never movement. All the other parts of this rigid body will have a rotation around this axis. So that is the definition of rotation around a fixed axis. So there are a lot of examples you guys can find in our daily life. So here we can call that a system of gear, or gear system. We call that in Chinese 齿轮系统. You know, we call that this is the tool, gear. You know, gear. Gear. So actually, we have talked about the relation between two gears, which is I1 second will equal the angular velocity of these two gears, omega 1 over omega second. It always equal the number of the gear. You know, we use this letter Z to denote the number of use this Z second means the number of gear second, and Z1 means the number of gear one, and this ratio will always be a constant, right? It will be a fixed number. So that means the ratio of two gears is rotational speed, or angular velocity will always equal a constant value, right? So that is actually our car. When you are driving a car, you can choose a different gear. We call that 档位. You have a lot of choice to maybe to make your car move forward or move backward, just to shift some gear on a gear system. And here we can see it is the wind turbine. So you know, actually, since there are a lot of government, especially China, are trying to fulfill the climate, right? To protect the environment. So all the world famous main country are trying to develop maybe electronic car, 电车, you know, we use this healthy power wind turbine, decreasing using the coal, right? And fair electric. So this is 风力发电, right? Wind turbine. And this door, you can open it, you can close it. Actually, this door also can be treated as a rigid body. It will round this axis to have a rotation around the fixed axis, right? After we know the definition of rotation, we should know the rotation equation. So there are three things, you know. So when we talk about the rotation equation, actually we have the angular displacement. So maybe we can use letter C, we can use letter phi. We also have angular velocity, right? Which is omega equal d theta over dt. We can use theta 1 dot, right? Another is angular acceleration, which is derivative calculation of omega. So I think this you guys should very familiar with this. So that is all the rotation equation about, right? And we can have this very useful formula about the uniform rotation and rotation with the uniform angular acceleration. So when we talk about uniform rotation, that means alpha, that is angular acceleration equals 0, right? If angular acceleration alpha is not 0, then we can think about maybe it is a rotation with uniform angular acceleration. So a body has a uniform rotation when omega is constant. So if and rotation with constant angular acceleration when alpha is constant. So this is a very useful expression. So I think it's very interesting is we can deduce this or we can prove that this expression is true if we know this and know this. So you can find if angular displacement theta equal omega 0 times t plus half alpha t squared, then you can try to use the derivative calculation. So when we do a derivative to time t from the both sides of this equation, you can find the left side will be theta dot, which is d theta dt, actually is omega, right? And omega 0 times t dt, it will just left omega 0, right? And alpha, we just write at here, and t squared, its derivative calculation will be 2t, and 2 times half will be 1, so this is alpha t. You see? So when you do this derivative calculation, you come from this expression of angular displacement into angular velocity, right? Actually, we can do the derivative calculation further. So omega dots actually equal alpha, right? And the right side of this will be 0, and this will just alpha. So we have this alpha equal alpha. That is a body has a with a constant angular acceleration. So back the direction, we can use integral calculation to have, so omega will equal omega 0 plus alpha t, and theta will equal this. And how can we get this expression? It's very useful and it's very simple to prove that. Actually, we can write this omega squared, will just equal these two atoms sum, it's squared, right? Alpha t. And then we can find, we have omega 0 squared plus 2 times omega 0 alpha t, and alpha squared times t squared, right? And we can try to simplify this expression to just write as like this, omega 0 squared, and we will take the common 2 from 2 alpha from these two atoms. So we have plus 2 alpha. Then the first atom of this will only have omega 0 times t, right? And this one will change into 1/2 alpha t squared. So which is very interesting because you can find actually this part actually is theta, right? So that's why we have this expression omega squared equal omega 0 squared plus 2 alpha theta. So I think this process of proof is very interesting. So I show you guys again. Actually, these three formula is very important. You should know that. And we also focus the kinematics of a point in the rotating body. So if you guys still remember, actually, from chapter 8 and chapter 9, we will use the kinematic information of a point on a rotating body all the time, right? So please you guys think about that. The path of a particle in the rotation body is a circle, right? As shown in this figure. So this is the rigid body. This is its axis. This body will have a rotation around this axis. So you can arbitrarily select a point on this body. If you look from this direction downward to that, you will find. So maybe we have a God viewpoint, 上帝视角, right? God viewpoint, am I right? We think we can find the trajectory of any point on the rigid body. It's hard to write something. We will definitely find actually this point B will always around the fixed trajectory. That is a circle, right? So back to chapter 6. Do you guys still remember when we know a point will always along a fixed trajectory, we'll naturally think about we should use the natural coordinates system to denote its kinematic information. So that's why we use this actually R coordinate actually is natural coordinate, you know? So we can select this is the reference point. So after some time, we can have this theta actually, let's say, we will have our length of this arc will just equal r theta, right? And because we are using natural coordinate system, the velocity only have one component along the tangential direction or tau direction, so which is s dot tau direction. And s dot actually is r theta dot equal omega. Actually, it will be omega r. See? Do you guys see this? That's why, let me finish. About its acceleration, you know, about this point B, its acceleration, it will always have two components. One is AT along the tau direction, which direction is the same direction with the tau with the velocity, right? So we have AT along tau direction. We also have AN, we call that AN, N means normal line. So because this is circular path, so this O is its center, right? So this is normal line because this point and this line will perpendicular to the tangential line and point to its center, and this N direction. So you guys should once again remember that AT actually should equal what? Should equal V dot here, V dot here. So V dot actually is this dot, and omega dot actually is alpha. So this is why tangential component AT equal R times alpha, and alpha is angular velocity, right? And our AN will always equal V squared over rho. And this rho is curve radius, curve 曲率半径 curvilinear radius of this point. So this maybe it's a circular, maybe it's just a curved shape, right? And we can use actually here rho equal r and v equal omega r. So an always equal omega squared times r. So do you guys remember actually at chapter 8 and chapter 9, we use this information all the time. That's why if we know a bar like this, we call that OA. If we know it along this CW direction, it have an angular acceleration alpha. So any point on this bar, we can draw its velocity. So this is VB. Let's say this point is B. So this is VB. Its magnitude will always equal omega times R. And this R actually is the length of OB, right? We always use this conclusion all the time at chapter 8 and chapter 9. So back to here, we are reviewing what we have learned. So I repeat that again. I hope you guys can totally grasp all this knowledge point, basic knowledge point. And when you try to find the correct direction of VB, you should always think about you link OB, you prolong this OB a little bit, and you rotate that prolonged in part along the direction of omega. Let it rotate with 90 degrees. Then you will find that the correct direction of AB, and its magnitude will equal omega times R. Here R should equal the length of LOB, right? And we can maybe we should draw another letter. We have this, so we can give AB should have two components. One is AN, right? Another is AB. ABT, maybe this is ABN. So ABN will equal what? Omega squared R. The same like this, right? And ABT will equal alpha times R. So when we have the information, if we say that actually OA will have a uniform omega along this direction, that means alpha equals 0, then ABT will equal alpha times R equals 0, right? Then at this condition, we'll know actually any point on this rigid body OA will only have one part of acceleration. That is its absolute direction of its acceleration will point from this point to its center. No? So we use these information all the time. So you guys should better know this. So if you still have some confusing here, maybe you should read all the paragraph yourself after our class time. So I have to quick the speed because we don't have enough time to teach all these details again, right? So anyway, I hope you guys know this key points, right? And the other thing, the absolute magnitude of this A, the intersect angle between AT and AN is very easy to understand. So I think I will not repeat that again. So that's the conclusion. Maybe you guys can read it again and think about that. Can you totally understand that? So V is proportional to R, and its direction is perpendicular to R, right? It is defined as positive when its direction is the same as of omega. Actually, omega will always have its direction will totally according to the direction of omega, right? Because V equal omega R, so the direction of omega will directly directly domain the direction of V, right? And secondly, the angle theta between the resulting acceleration of any point and the radius through it is identical and less than 19. The distribution diagram of velocity and acceleration of rotating body are shown in these two figures. So one, so this is the rotating body who have CCW direction of omega. We can select 3 points to just give its direction of its v and calculate its magnitude with omega times r. Actually, you can find 3 points at different position will have different r. Maybe we call that r1, r2, r3, right? You should know how to find its correct direction. So that you can so you can prolong a little part and along the direction of omega, let this red line rotate with 90 degrees, you will find this direction. And you can prolong this a little bit and let along omega direction rotate with 90 degrees, you will find this direction. Also, this part you prolong a little bit, you along the direction of omega rotate with 90 degrees, you will find this. So this V3, V2, right? This can be V1. And this distribution of velocity, because the little the r is, the little the velocity is. So when the point actually coincide with the center O, r will equal 0. So the velocity will equal 0. So at this, the outer part of this maybe is the bar, or maybe the ball. So this will be biggest, and this is smallest. And this is biggest, and this is smallest. So you can think about all the point on this line, then you will have the distribution of velocity. We call that 速度分布规律. You know, maybe I can write it for you guys in Chinese. Distribution of velocity, we call that 速度分布规律, right? So you can find it's more like a word, a year, right? A leaf of a fan. Can you understand? Understand that? A leaf of a big fan. No, 一个风扇的叶片。So I think we have talk about the rotation around fixed axis. We talk about the wind turbine, right? We just said wind turbine, right? So it's more like that, right? It's more like that. So you guys can think about that. And this is distribution of acceleration. Actually, when alpha is not equal to 0, then you can find actually the absolute direction of this acceleration will always have an intersect angle with this link line between center, rotation center, and the point. And the intersect angle will always less than 19 degrees, right? Will always less than 19 degrees. That's true. That's true, right? Because when alpha not 0, then we will have tangent theta, right? We will have that tangent theta. Can you guys understand me? Tangent theta will always equal r alpha over r squared omega, right? Which will equal alpha omega squared, right? So that's the expression of this tangent theta, because it will have two components. One is AT, another is AN. So tangent theta will always equal AT over AN, which is R alpha over omega square R. It will be this, right? And here is the distribution of acceleration. So this is when the direction of alpha is the same to omega, then you will find these two figures are the same. So if the direction of alpha is not the same with is opposite to the omega, then this will be changed accordingly. So you guys can think about by yourself. About the vector representation of kinematics, we will just skip it. It's not very important for you because it just try to tell us when we talk about d let's say I is the uniform vector direction. Di dt actually equal omega cross product I. And this is very difficult to explain to you guys. It's hard to understand. So I think I better just skip this. It will not influence our understanding of chapter 8 and chapter 9. So I try to quick my speed, but I just spend about 40 minutes to review the chapter 7. So I hope you guys can review this whole textbook and try to understand. And then you can take some time to look some example by yourself, right? We have a lot of sample examples. You guys can look this by yourself. We don't have enough time to repeat it. Then we'll move to the chapter 8, right? We'll move to we will move to chapter 8. You guys to remember, actually, this is our homework. We have finished to do this, right? And let's see. Chapter 8, we talk about composite motion of a particle. Actually, in Chinese, we can write that 点的运动合成. So a particle actually is the point or 点的复合运动. Just use 点的运动合成, right? We try to talk about composite motion of a particle. So maybe we can review the basic concepts of a composite motion of a particle. So, in previous two chapters, that means chapters 6 and 7, we have studied the motion of a particle or a raised body in a fixed reference system. However, when we often observe the motion of a body from different reference frames. For example, we can observe the motion of raindrops from a traveling car or on the ground. The path of a raindrop is a vertical line with no wind when we observe it from the ground, right? But a slanted line when we see it from a moving car. So this is a very common phenomenon. Maybe all of us has encountered this phenomenon. If you are very curiosity, when you are sitting on a car, you look at the window, maybe there is a raindrop. You will find actually when you are sitting in the car, its trajectory is quite different to when you just stand on the ground, right? Why can we obtain different results when we observe the motion of the same object? Actually, the movement or the motion of the same object will not change. It will independent from where we are standing on to look at that object, right? But our description of a same object, we are trying to describe its motion pattern, will totally according to the reference frame we are sitting on. So that's the key concept of the composite motion of a particle. Actually, why we are going to learn these concepts of composite motion of a particle, actually we are going to use this relationship to find the relation of different related bodies in a same body system. So please, you guys think about what I'm talking about. So we are going to study the relationship and the difference of the motions of an object relative to a different reference frames, and to establish the relations of velocities relative to different reference frames, as well as acceleration. So when we are talking about this, when I finish this reading of this paragraph, I just think about the typical example we have learned together. So I can draw you guys here again, right? So let me draw a very typical example here. So let's say if we have this, it's hard to draw a picture on this file, so maybe it will take some time. So if we have maybe these two fixed points, O1 and O2. So I think you guys should be very familiar with this kind of expression. Actually, we use this to denote. Actually, uh, uh, it means, let me try to give you. Do you guys remember, actually, we have used this example to talk about the basic concepts of composite motion of a particle, right? So let's see this. Now I will change another color. So actually, let's say this OA is the rigid body. It will have a uniform angular velocity omega, right? Then this is a very typical example. So we select point A as our moving point. Do you guys still remember what is the moving point? See, I don't have many choice. It's correct. So A is our moving point, right? And we select MCS. You know, our MCS is the moving coordinate system fixed on O1C. And our SCS, do you guys still remember what is SCS? Stationary coordinate system, always is 大地 Earth's ground, right? It's Earth's ground. Then the same point A, we'll talk about that. So first we'll talk about its velocity. So we have VA equal VE plus VR. Do you guys still remember these three terminology? So these three terminologies, because this VA, A means absolute velocity. That means moving point A is movement when we are sitting on the Earth's ground. It's more like we are just sitting or standing on the Earth's ground, right? We look at this point, we will find actually this point A is absolute movement will be rotation around the fixed point O2, right? A trajectory will always circle with its radius will O2 A. Let's say it's R, right? Let's say L O second A equal R. Right? So since VA is the absolute moment of this moving point A, so it is the point on the O2 A. Do you guys agree that O2 A actually is the rigid body around the fixed axis O2, right? So we can just actually this should be a horizontal direction. So we will have actually VA will totally perpendicular to this O second A, and this will be VA. And its magnitude will equal what? We just reviewed that will equal omega times LO second A, which is R. See, we just review that, and then we use this expression here. The second is we call that transport velocity. So this is very hard to understand. I repeat that many times. So I should repeat once again. You guys should listen carefully. We always think we have a prime, we have a prime which is coincide with a moving point A, but this A prime actually is a point on MCS, right? Actually, A prime, you can think about we have A prime at this time moment. Its position is coincide with the point A, but actually it is a point on O1C. Actually, this is typical body system. When O second A have CCW direction uniform angular velocity rotation, actually this guy will have the same rotation. We can give it omega 1. Maybe also have angular acceleration alpha 1, right? So that we call that transport velocity. In Chinese, we call that 牵连速度. Absolute velocity, we call that 绝对速度. So you guys listen to me carefully. Since A prime is a point on O1C, and we know O1C will have another rotation around the fixed point O1. So this VE, it will equal omega 1 times LO1A, right? Times O1A. When we are doing our calculation, always this angle will be known. Then we can easily from the length little r to find this O1A will just equal r over sine theta, right? So I will not do that calculation again. And you should know its direction. Maybe I should change another color. So you see, actually, because this A prime is a point on O1C, so its direction will perpendicular to, this is not good color, but this is our VE, this is our VE. Its magnitude will equal omega 1 times LO1A, and its direction is because we know the direction of omega 1. Then the third one is the relative velocity, 牵连相对速度. You once again, you can think about that you are sitting on O1C. You just look at this sleeve, right? Because this is the rigid body, it has an internal hole, and this O1C push into this hole. So this sleeve will move along this direction. It will have relevant movement. So when we are sitting on O1C, we will find actually this sleeve have a translational movement along O1C. So the point A also is a point on this sleeve. So it will have a VR, right? We call that VR is relative movement or relative velocity VR. So because this VA equal VE plus VR, we should always to make sure that this VA should in the position of diagonal position of their parallelogram, because this VE and VR will constitute a parallelogram. We should make sure VA in the diagonal line position. So that's the true. And if this is theta, so this is theta. Do you guys remember we have learned this? And this the second, maybe third time I repeat that. So we will find through this expression, we find the relationship between absolute velocity VA, transport velocity VE, and the relative velocity VR, right? Actually, we can easily find actually VA times sine theta equal VE, right? And VA times cosine theta will equal VR. So if we know VA, then we can find VE. Because VE equal omega 1 times LO1A, then we can find O1, omega 1, right? Another time, if we know VE, then we can find VA. We just use VA over sine theta. We can find VA. Then because VA equal omega times R, then we can find omega, right? So according the different known quantity, we can find another quantity because this equation we have three atom. Each atom have direction and magnitude. Actually, we have 6 quantities. If we know 4 of them, then the other 2 of them we can totally find out, right? That's what we have learned, basic concept of composite motion of particle. We are just finished to talk about the velocity, and we will keep to talking about acceleration. And it is time for us to have a short break. We will restart at 11:11. So all you guys, please have a short break. Okay?
Okay, Laksh.
Okay, everybody, let's continue. So I think we just finished talking about the theorem of velocity composition, right? Uh, Actually, we have VA equal VE plus VR. So this is absolute velocity, and V is transport velocity. Actually, it is the point which have the same position with the moving point, but it is on the MCS. And this VR actually the moving point is relative moment to the MCS. So it's very difficult, and this is very important relationship. We can use this relationship to find uh, from this typical body system to find the relationship between one rigid body to another rigid body. So actually, you guys can think about that. Actually, when this OA have a uniform angular velocity along this direction, and this O1C, you have to oscillation. Oscillate, I mean 摆动. Actually, it is another rotation, but will not rotate with the full 360 degree. So O1C will rotate around this point O1 from this position, maybe the leftmost position, maybe here, then back to the rightmost position, right? So this are oscillation. This oscillating or swing from one position to another position, totally because of the O segment A, right? Actually, it is the relationship between the different rigid body of the same body system. So we must know this relationship. And second, I'd like to review that we have learned the relationship between the these three, more like this, but we can write as, can you guys still remember we have AA, right? Equal plus AE plus AR and plus AC. Actually, this is expression of composition theorem of acceleration, right? Acceleration. So this is absolute acceleration of this moving point A, and AE actually is A prime. It is its acceleration at the same position. And AR is the relative acceleration of this moving point relative to the MCS. Here is O1C. And this AC, we call that 柯氏加速度, 柯里奥利. So this AC will equal 2 times omega E. Omega E means moving coordinate system with times VR. So you guys should remember that when our MCS is we'll have two types of simple radial motion. One is translational motion. So when we talk about our MCS is translational motion, then it's omega E will equal 0, right? Omega E equals 0. Then we do not need to consider acceleration, right? When our MCS like this example, O1C, it has rotation, fixed rotation movement. So it will have omega E. So here you guys can find, so here in this example, we will have to consider AC, 柯氏加速度. It will equal 2 times omega 1 times VR here, omega 1 VR. And if there is the AC we should consider, we also should learn how to find its correct direction. I will tell you guys again. I hope you guys can remember that. So when you try to find the correct direction of AC, you only need to find the direction of VR, So we find VR here. Then you let this VR rotate around the point A along the direction of omega 1 with 19 degrees. That means you will find the correct direction of AC. So let's say it's very complicated. I hope you guys have impression is enough, right? You only need to have an impression. I do not need you guys must grasp this part because it's too difficult for you guys. But I will try to show you guys how to find this relationship. So let's say I will change the color from time to time and tell you. So first, let's according to this expression and draw all the components of each acceleration on the same figure because this is very mass. So we better select another position like this to draw all the thing. So first, let's say OA has a uniform angular velocity omega. That means it only have one acceleration component. That is AN. AAN, right? AAN. Then it should equal omega squared times R. And its direction will from A point to A 0 second. No? So this is AA. I think this part is still very difficult for you guys to totally understand, but please pay attention to and listen to me carefully and try to understand. And if you try to understand all the details, maybe you should read this whole chapter again. And then AE, AE actually is A prime. It is a point on O1C. And O1C has this omega 1 and this we assume this direction of alpha 1. So it will have this, we call that AET, right? Transport acceleration AET, which will equal alpha 1 times L O 1 A, because actually A prime is coincide with A. So LO1A actually is LO1A prime, right? Another is normal line direction component of acceleration. So we also have this is AEN, which should equal omega 1 squared times L O 1 A. Then I change another. We just along this VR or opposite this direction of VR to give its AR. It's quite easy. So this is AR. So once again, the final thing is how to give the correct direction of AC. We know AC magnitude is 2 omega 1 VR. Actually, omega 1 and VR we have find from these expressions, right? And so first you find the VR, then you along the direction of omega 1. Let this VR rotate around point A with 90 degrees. You will find actually our AC actually is very coincidence. It's just along the same direction of AET, right? So this is AC. So after you draw all this, maybe some component is known and some component is unknown, then you can use the production method to find out the unknown quantities one by one, right? So a very useful trick is when you are trying to find some unknown, you should try to select the appropriate axis to project your equation onto that axis. So let's say let me give you an example. If we are trying to find like AET, we try to find alpha 1. So actually the best choice, we can select this as conc1. No, as this conc1, we can project the whole equation of this one onto this axis. Why this is the best choice? Because you guys can find AR and AEN all perpendicular to this conc1. Then when you do your projection, all these two components will have zero component onto this conc1. So we only need to, let's see if this is theta and this is theta. Can you guys still follow me? I think it's too difficult for you guys. See, although I repeat this maybe third time, but it's still very difficult for you guys to understand, right? So if this true, don't worry about that. I only need you guys have some basic impression of this acceleration. Is okay, right? It's too difficult for you guys. So when we do this projection, you know, at this conc1, so we will write like this. We will have AA cosine theta, AA cosine theta equal, you know, this AE has two components. One is AET. It's just on the conc1, so we can just write AET. And you find AEN, although it has some magnitude, but it's perpendicular to this conc1, so we do not need to consider it anymore. And this AR actually also perpendicular to this conc1, so we do not need to consider it either. And we only had another AC, which is along this direction, so we give AC. You see? So when we select appropriate axis, when we do the projection, use the projection method, we can just simplify this whole expression. Then if some quantity is known, and then the unknown quantity will be fine. So AET equal alpha 1 times LO1A. If this AA, actually we know AA, we know AC, so we can find AET, then we can use AET over LO1A, we can finally find alpha 1, right? That's how we use this method. That's so-called composite motion of a particle. We just use this relationship about velocity and relationship about acceleration to tackle the problem of a whole body system. Let me give you guys another example. Actually, here the problem just is the problem from the medium examination of my Chinese student. Let me show you guys. I think it's very easy to understand. So actually we have a problem like this. So this is bar OA. And we have rect bar like this. Let's say this is C, and this is B, and this is D. So we know this rect bar CBD actually is the whole rigid body. It has a translational movement with velocity, v, and direction. So uniform velocity from right to left. So you can see actually this rect bar BCD will push this OA round along this direction. Let's say this is O1, right? So if we know the length of BC with L, so can you guys find the method to find the omega 1? Can you guys think about that? So I'll show you guys, again, we are just use this velocity relationship between. So first we should select C as a moving point, right? C is a moving point. And we select OA will be our moving coordinate system. So please, you guys, please think about that. When you are sitting on OA, you look at this point C, what can you find the relative movement pattern will be? Actually, when this BCD move from right to left, it will push this OA rotate around the point O, change its position. But if we are sitting on OA, we will cannot find the rotation of OA. We will more like to find XC, point C is translational move along this OA, right? So actually that is the relative movement. And our Earth ground, maybe we do not write it in our SCS. That is all the Earth ground fixed, right? Fixed. Then you can just use VA is absolute velocity of moving point equal transport velocity VE plus VR. Let's say before we do this, let's say this angle is we known in advance is theta, and this theta equal 30 degree, right? 30 degree, and this is rectangle, 90 degree. So you guys can find actually because this MCS is rigid body BCD, it has a translational motion, right? It has a translational motion. That means any point on this BCD will always have the city of this way. So actually our VA will totally along the same direction of V. It's hard to draw this. I will try again. Maybe I can draw a straight line. So can you guys understand? So this actually will be our VA, right? So this is VA, and its magnitude will equal V, right? This VA will equal V. And since we know when BCD push OA like that from this direction, from right to left, then it will along this omega 1 direction, which is CCW direction. Then we can think about a C prime, right? C prime coincide with point C, but it's a point on MCS, which is OA. So it will be perpendicular to OC here. Maybe I can draw a straight line. Maybe I can change the color. So this is, oh, I cannot use this to draw a straight line. So I will have to draw by myself. I hope I'm lucky enough. So can you guys understand? Actually, this is VE, right? And VE will equal omega 1 times LOC. Since theta equals 30 and BC equal L, so the 30 degree, so this OC length will be 2L, right? See, this omega 1 is we are trying to find, so we just need to find VE is enough. And VR again. So can you guys understand? We know actually C will have a relative movement along OA, maybe direction of CO, maybe direction of CA, but we know it must be the direction of CO. Why? Because we have the rule. We have to keep this VA always on the what? On the diagonal line position, right? So this will be VR. So if this theta and this is theta, so we will have this three vector VA, VE, and VR will constitute a rectangle triangle, right? So this will be VE, and this will be theta. So you will find actually VA times sine theta. Actually, which is half because theta equal what? Equals 30 degree, equal VE. VE equal omega 1 times 2L. So VA equal V sine theta equal a half, right? And omega 1 times 2L. Then our answer will be omega 1 equal what? 4L and V. So can you guys understand this problem? Because this is very simple compared to the first example. Because here our MCS actually has a translational moment. And here our MCS actually has a rotation moment, right? So if you guys can totally understand these two examples, then all the things we have learned from this chapter 8, you will understand totally, right? So can some guys of you can understand this example? Can you guys understand that?
Yes, Laos, yes.
Okay. If that is the case, I will very happy because I hope you guys will understand it a little bit more, right?
Okay.
Okay. Then we'll move to chapter 9, right? We have finished all the contents of chapter 8 just through these two typical examples. So you guys, if you can take your time, can look at the whole contents of this chapter 8, will be very helpful to your understanding because there are a lot of examples on the book, but we don't have enough time. You see? This is more like I just join here, right? I just join here. So you guys can choose your appropriate time to read all these things again. If you don't, that's fine. That's fine. Okay. So I think the final part is in chapter 9. So there are a lot of typical examples you guys can look at it, try to understand. Some of them is enough. And let's see. This is final chapter 9. You see, actually this 8 to 3 is our homework. We have finished. We have talked about that together, right? And this also is our homework, right? It's also our homework. And so back to chapter 9 again, we talk about plane motion of a raised body. So actually its main focus also is what? Also is the mechanism. Actually, we call that is the body system. Because you guys still not learn another course called the principle of machinery. Let's see this. I can draw a typical example here. So if we have a slider here, you see that this is O A. It very difficult to draw this picture very beautiful. So I hope you guys can understand. I will try my best, but it definitely very hard. And so let's see, this is O. If this OA also has a uniform angular velocity with omega, so you guys will find actually if this OA rotate like this, then this sleeve C, right? Or this sleeve B, it will move along this horizontal trajectory, left and right, left and right, 往复运动, right? So from the pattern of movement of a raised body, we can see body OA. It will have translational movement, right? And the sleeve B, let's say slider B, we can call that a slider because it moves along a fixed trajectory, left and right. So you can see actually because OA will around the point O have a circular trajectory. So you can see when A to this A prime, then this letter B will move to the leftmost, right? We call that B prime. And the next time when OA along the direction from here rotate to here, then when A at this position, we call that A double prime, maybe here, then our slider will be rightmost position. Let's say this is B double prime. See, so we can link this B prime to B double prime here. So we will call actually this H of slider B. Because when OA with the uniform angular velocity omega around the point rotate around the point O with revolution and another revolution, then this letter B will move along this fixed section of line, left and right, left and right. Can you guys understand my description of this mechanism? Right? So this letter B.
Yes, 老师。
Yes. So now, so this letter B, what kind of motion it will be? It will have.
Translation.
Yes, definitely. Great. So this letter B will be translational motion. So you guys can find actually teacher Fang didn't mention AB, right? I deliberately didn't mention AB. So you find actually AB do not connect with fixed frame directly. So at point A, it link with OA. At point B, it link or connect with letter B. So actually this AB will have the most complicated motion. That is plane motion, right? This is the plane motion. So let me tell you guys how to understand this plane motion. So back to the first part statics, we have talked about the constraint force, you know? So let's say we have a fixed coordinate system, X and Y. So if we have a free body, let's say it's free on this plane, that means it only can move at this plane, X or Y, but it's totally free. Then you can think about this raised body A will have three kind of movements. So one is translation along X, right? Another is translation movement along Y. And the third will be rotation around some axis. So this is a raised body, totally free on the plane. It's free. So its freedom equal 3. So here 3 means it have three types of independent movement or independent motion. So you can see direction of X and the direction of Y is perpendicular to each other, right? Let's say this direction is CCW direction omega. You can use our right hand rule. So our forehand folding like this direction of omega. You will find actually this omega will point out of this plane. So next time, if you tell me that your omega actually is the CW direction, then it will be perpendicular to this screen, but push into the screen. Any case, it will have the same conclusion that the direction of omega also perpendicular to x and y, because it's perpendicular to this plane, then it will perpendicular to any line on the plane. So that means the three vector, one vector is omega. So let's say the direction of omega A, we use this arrow to mean its direction, and x direction and y direction will perpendicular to each other. So these three kind of movement, or this three kind of motion is independent. Independent 是独立的。Can you understand? 独立的 means it will not influence each other, right? So it can happen at the same time. It also can happen successively, because the three components of movement is totally independent. So that is free body on the plane. The next time, if we have some kind of measure to let this body, it only have rotation movement. That means it will be fixed on maybe just pinned here, like this A. No, we pinned. Am I right to describe this? Maybe we just use the nail to push this body into the plane. So you can find it only can rotate around the point A with omega, maybe also have alpha. You see, actually this one is what? Is what we have talked about rotation around the fixed axis, right? It's one of the typical simple motion of a rigid body. And the second, we can think about another case. That means this body A, it can move at this plane in any direction, which can be divided into two directions, X A and Y A, but it can never rotate. You know, actually, this is the definition of our translational movement of a rigid body, right? So this is a reference line. It never change its orientation, right? So this is translational movement. Translational movement. See, if this is totally free on the plane, then it will have three kind of component of motion. So we have two translational movement components and one rotational component. That is plane motion, right? That is plane motion. You see, actually OA, it is fixed on point O, so it only have rotational component. And this letter B, it only can move along the X direction, right? It cannot rotate because the constraint of the maybe polished ground, right? So it will have translational movement. But this AB is not connected to the frame directly. So the frame cannot constrain AB anymore. So this AB will have plane motion. Then plane motion will have three independent movement. Two is two translational movement, X and Y. Another is rotation, right? So that is introduction to the plane motion of a rigid body, right? So maybe I should read this whole paragraph to you guys again. Plane motion of rigid body is often seen in engineering, especially in some famous or typical mechanisms, right? And it's more complicated than the basic motion of rigid bodies. So you can think about that. Plane motion is rotation plus translation. because these two also independent one to each other, right? So you can think about that. It is more complicated than the basic motion of rigid bodies. Investigation into this kind of motion is conducted on the basis of translation and rotation of a rigid body using composition of motions. 运动的合成 composition of motion. So decomposing a plane motion into translation and rotation components respectively, and employing the theory of composition of motions. The formula for finding the velocity and acceleration of points in the rigid body can be derived. See? So if you guess, try to think about what I have explained to you guys here today. Actually, we can treat this plane motion. It can be looked at two components. One is translational movement, another is rotation movement. And these two components is totally independent to each other. That's why we can use this composition of motions, right? So we have finished introduced definition of plane motion of a rigid body, and we can talk about the plane motion. It's what? Its functions. Let me show you guys again. Actually, we have this. So I can draw a coordinate system again. This O, X, Y. So let me change the color and I draw an arbitrary shape to show you guys that it is the body B. And if we know this body B is free on this plane, so it will have what? It will have plane motion. So we can arbitrarily select a point O prime as the pole point. Do you guys still remember what is the pole point? So we can think about that. We can fix a translational coordinate movement, a coordinate system x prime, O prime, Y prime here. Which means this x prime, O prime, Y prime will totally along with the translational movement. But when this rigid body B has or proceed its rotational movement, then this x, y, O prime, Y prime will never rotate with its rotational movement. So that means we can link this. That means if we are sitting on this x prime, Y prime, any arbitrary selecting point A on the rigid body, we can find it's more like it rotates around this O prime because we are sitting on the O prime. So actually we have the so-called pole method. I will repeat that again. So first we are talking about the equation of plane motion. So we can link that this O prime. And if we have next time this x prime will have rotation. Let's see, we have a reference line. Let's see, I will change the color. Let's see, we have a reference line here. Let's say OM. O prime M. So you can see if I draw this. So maybe it's very ugly, I'm sorry, but I try to explain myself in this. So you can see we have a vector loop, which is OM. OM means vector on the SCS and equal what? OO prime. It's OO prime plus O prime M, right? You see, when this rigid body have its translational movement, then the position of O prime will change with the time change, right? So this is O prime, OO prime. And when this related body has its rotational component happens, then the orientation of this OM to the fixed axis X, Y will be changed. So the equation of a plane motion can be read as this: XO1, I'm sorry, XO prime equal F1t. Maybe it is a function of time t, right? And YO prime equal F second t. And another is the phi will equal omega t. So the first one is the translational moment. See, translational moment XO prime and Y prime. The third one is its rotational component, right? Actually, that of a plane motion. And then we are going to talk about the composition, right? A decomposition of plane motion is this. You see, we have learned this. This is more beautiful than I just drawing on the screen, right? So actually, this A is our pole point. So we have equation of a plane motion will be xa equal f1t. It is a function of time t, and also a function of time t with xa and ya. Actually, this is two translational component of its whole plane motion. And the phi equal f third t. It is another function of time t. This is rotational component. And our plane motion can be decomposed into translation and rotation. Can you guys understand this title until then? Because I try my best to explain to you guys again and again, right? So that means we have we can think about when this rigid body have plane motion, actually its translational component, its rotational component happens simultaneously, 是同时发生的 happens simultaneously. But because this translational component and this rotational component is totally different, is totally independent from one to each other. So we can imagine actually these two components is happened successively. You know, if we think about that, we can further simplify its motion analysis without influence the final result, right? So when we only consider its translational moment, then this body this time is only a translational related body. And when we just think about its rotational component, then it changes into a fixed rotation moment, right? So we call that 运动叠加原理. Although these two components happens simultaneously, but we can think about that it happens successively. Can you guys understand me? So if we can use this method, then its complicated motion can be decomposed into two simple components. One is translation, another is rotation, right? So that's why we have the velocity of a point in a plane figure. We have this, right? We have this. So I can write as this. So any arbitrarily selected point Vm, we use this O as is the pole point. So we can use Vm. It's more like its absolute velocity will just equal VO, means it will totally along with VO with the same direction. Then it also have a rotation component around O, VMO. Right? And VMO always equal omega. Omega is the angular velocity of this rigid body, because it had plane motion, then it have to have the omega. So omega times LOM, length of LOM. So if we know this VMO first, then we can find omega. If we know omega first, like this figure, we can find VMO. And this VO and this VMO will constitute what? A parallelogram. Then we should always make sure VM will be diagonal position. Just like what we have learned from chapter 8, VA equal VE plus VR. So actually our VA here is VM. Our VE actually is VO, because this X prime or Y prime will never rotate with along this rigid body, but will move along with this body. So this VE actually is the velocity of VO. And this VR actually is VMO. It's more like we are sitting on this X prime Y prime. We look at this point, we found that it will rotate around the point O, right? So if you guys know this, because today we don't have enough time to cover all the details of this final chapter 9, but I highly recommend that you guys come back to this chapter to look all the paragraph here, our textbook, and trying to think about some a typical example. Then you will find you have insight, understanding, right? A deep understanding of the whole chapter. Because that is base point method, actually also called the pole point method, right? Pole point method. So this concept is different from our PPT, but it's the same thing, pole point method. And we also have another thing, you know, we talk about the projection method. So last time when we are discuss our homework, some guy of you let me explain projection methods again. So it's very easy to explain, right? So when we projection this equation onto the direction of like OM, right? So if this is gamma, so we will have, because OM means VM cosine gamma. We just draw equal sign here, and VO have theta, and VO times cosine theta. And you can find VMO always perpendicular to this direction, so its projection always 0. See, that's the projection method. If you know 2-point is direction, then you can 2-point velocity direction, you can link this 2 point. You find this direction of 2 intersection angle, then you can use this projection method. If you know VM cosine gamma, you know cosine theta, then you can find VO, right? Otherwise, if you know gamma, theta, and VO, then you can find OM, right? The final is the acceleration. We also have AM equal AO plus AMO. But this OMO, because it is a rotation, it have 2 parts, one AMOT plus AMON. So once again, the composition of acceleration may be too hard for you guys. So maybe you cannot review this. We do not need you guys must grasp all this. I only need you guys have a typical an impression is enough, right? So if you don't have enough time, you cannot cover this. I think that's all for today. I used 2 classes today, just review the chapter 7, 8, and 9 again. I hope I can a little bit help you guys to learn a little, to understand all the content a little bit more. Okay, I think that's all for today. We don't have homework today. 那么今天就上到这里吧，好不好？
Thank you, 老师。
好嘞，下课吧。 再见，
好，教练，是，thank you。
再见。Hope you can understanding more.
Yeah，老师。
OK，拜拜。
OK，拜拜，再见。
Okay, I'm too tired.